Great, thank you. All right, this is joint work with Ahmed and Chris. So this talk will be about some connections between statistical physics and computer science. And in particular, I'll be talking about these high-dimensional inference problems. So here are some examples of these types of problems. Roughly speaking, there's some kind of a hidden planted signal, maybe a vector, and we get to observe this signal through some kind of a noisy channel. So maybe it's a clique hidden in a random graph, or a low-rank matrix corrupted by additive noise, etc. And these are all inference problems, so we'd like to infer the planted signal. And there is an intimate connection between these types of problems and statistical physics. And the connection is essentially that for these inference problems, the posterior distribution of the hidden signal given the observed data follows a Gibbs or Boltzmann distribution. And this is the same type of distribution that would show up in physics if you're studying some kind of a disordered system. Think of maybe a magnet or a so-called spin glass. And so in order to understand these Gibbs distributions, the algorithm belief propagation was independently invented in both communities. So in physics, it's called the cavity method. Roughly speaking, this is some kind of an iterative algorithm where you have variables, the unknown variables that you want to figure out. They each keep track of some belief about what they think about their own value and pass messages to each other and then update these beliefs in sort of a Bayes optimal kind of way. But I won't get into the precise details of this. But this belief propagation is a bit complicated and hard to analyze. And so a major breakthrough is this paradigm called approximate message passing, introduced by Donahoe, Malecki, and Montanari. And this can be thought of as a simplified version of belief propagation that is amenable to rigorous analysis. And with this, one can get extremely sharp results. So often the best possible mean squared error you can get is some constant, and AMP will exactly nail that correct constant. And other problems have these precise phase transitions, where as the parameters of the problem change, suddenly it will go from impossible to possible, and AMP will work all the way up to these transitions. And in many settings, we know this is the statistically optimal thing that you can do. So this AMP algorithm has been so successful that when it doesn't work, this is often taken as pretty good evidence that maybe no algorithm can work. And so by investigating this, we can get evidence that certain problems have computationally hard regimes. And so this theory, coming from statistical physics, really has been hugely successful for a lot of these different high-dimensional inference problems at very precisely understanding exactly the statistical limits and also the conjectured computational limits for many problems. But of course, this is not the only theory that achieves such a thing. Perhaps a competing theory is what's called the sum of squares hierarchy. So this is a systematic way to obtain convex relaxations of polynomial optimization problems. Note that basically any problem can be written as a polynomial optimization problem. And so this is a hierarchy of increasingly large SDPs. It takes about n to the d time to solve the level d relaxation. But as you go to these higher levels, you also gain more statistical power. And this also has been hugely successful, giving state-of-the-art algorithms for all kinds of problems like the ones listed here. And like statistical physics, sum of squares has its own way of arguing when problems should be hard. There's these SOS lower bounds, so you can prove that sum of squares cannot solve a certain problem, and this is often taken as pretty good evidence that maybe no algorithm can do it. So there's kind of a natural meta question here, which is to unify these two approaches, right? Statistical physics and sum of squares both have their own ways of predicting when should problems be easy, when should they be hard, and it's natural to know whether these predictions are the same and whether we can unify all of this. And so I don't have an answer to this meta question, but this talk will basically be about a specific problem called Tensor PCA, where perhaps surprisingly, the two disagree. So this talk will be about understanding that and seeing how we can fix it. So here is the tensor PCA problem that I want to talk about. So essentially, the object you want to recover is this planted signal, which is a vector of plus minus 1 values. And the problem is essentially summed up by this sentence here. For every p variables, you get a noisy observation of their parity. Okay, so more formally, this p is the tensor order. It's just some positive integer. And then for every subset of size p, you get to observe this observation, which is some constant times the true parity of that subset plus noise. Okay, and this lambda is a signal-to-noise parameter. If lambda is big, this makes the problems easier. One can equivalently write this in tensor notation, where you observe this rank 1 tensor plus noise. This is essentially equivalent if we ignore the entries of repeated indices, which turn out to be not important. And perhaps you've heard of this spiked Wigner matrix model, which is just the case p equals 2, where you get to see a rank 1 matrix corrupted by noise. All right, so this is the problem. And okay, how should we solve this problem? Maybe the first thing to try would just be maximum likelihood estimation, where you can compute the posterior probability of any given vector, given what you observe, and find the vector that maximizes this. And one can show that this succeeds, provided the signal-to-noise ratio is above a certain threshold. And in fact, this turns out to be essentially the statistically optimal thing you can do. But of course, this is not efficient because you have to try all the solutions. So we would really like a polynomial time algorithm. And one class of such algorithms are what has been called local algorithms. This is a class of various algorithms, but essentially what they do is they keep track of a single guess, which is some vector of what we think is the true planted signal. And then you want to just locally update this, right? Change it to a nearby vector that increases the log likelihood. So this would include things like gradient descent, tensor power iteration. Langevin dynamics is like a continuous version of gradient descent. And then also this approximate message passing, which is this hugely successful algorithm coming from physics. And these succeed when lambda is above some other threshold, which is worse than the best one, the statistically best one. But okay, there's also a third class of algorithms here, which is the sum of squares. So either the sum of squares STP itself, or various spectral methods that were inspired by it. And even a much more simple spectral method where you basically just take your input tensor, flatten it to a matrix, and take the top eigenvector of this. And these succeed at some third threshold. And sum of squares lower bounds suggest that this is actually the correct threshold for polynomial time algorithms, in the sense that we don't believe polynomial time algorithms can do better. And so before we get confused about all these different thresholds, let me make a picture. So this lambda is the signal to noise, right? Increasing here. So when lambda is just too small, the problem is just statistically impossible. And then at some point, the maximum likelihood starts to succeed. And then we have this sort of hard phase where we know it's statistically possible, but we don't know an efficient algorithm. Then at some point, sum of squares starts to succeed. But the surprising thing here is that these so-called local algorithms don't succeed until substantially later. It's like a different power then. Right, so this is sort of the this surprising fact, which is maybe concerning for the statistical physics point of view, that this AMP algorithm, which has been so successful in the past, seems to be substantially suboptimal here. So this is maybe a bit puzzling. And so there's really actually a bit more to the picture than what I showed there. Right, I kind of was concerned about hard versus easy, but really there's a whole spectrum. I can think about algorithms of sub-exponential time, 2 to the n to the delta. And tensor PCA turns out to have this smooth trade-off, where if you want to tolerate the lambda being a bit smaller, you can do that at the cost of increasing your runtime to some higher sub-exponential. And so this can be thought of as sort of interpolating smoothly between the polynomial time and the exponential time. All right, so all of this is happening in the hard regime. And so I'm talking basically about how hard precisely is it. And what I'm saying is that as you go from sort of polytime to exponential time, it smoothly gets harder. This is not necessarily the typical situation. Many problems actually have a sharp threshold, where it's polynomial time, and then suddenly you hit a wall, and it becomes conjecturally exponential time. And so this is actually kind of going to be important here, because of course, if you have a soft threshold like this, well, we can't really expect belief propagation or AMP to be optimal, or at least for them to not be the end of the story, right? Because those algorithms are essentially linear time, whereas in situations like this, we expect you can do a little bit better by moving to slightly bigger algorithms, say quadratic time, cubic time, and so on. So really, we would like a hierarchy of increasingly powerful AMP-type algorithms. Okay, so this is a little bit of an aside to talk about something else I think is quite exciting that's also related to this. So we saw this sub-exponential trade-off, and I want to mention that there's evidence that this is actually the best possible trade-off you can achieve, in the sense that any algorithm of this sub-exponential time cannot tolerate signal-to-noise better than this. And this evidence is the form of what's called this low-degree likelihood ratio, which is a relatively new and I think quite exciting conjecture. So it's a fairly simple calculation that seems to predict how easy or hard problems are. It came originally from sum of squares, in particular from Hopkins and Stoyer, and was motivated by this so-called pseudo-calibration approach. But it's much simpler than sum of squares to carry out this kind of calculation. And the idea is extremely simple. You just ask whether there's a low-degree polynomial that can solve your problem. And by solve your problem here, I mean the hypothesis testing question of, I give you a tensor. Either it's the spiked tensor with the planted signal, or it's just a pure noise tensor. And you would like to find a polynomial that can tell the two apart. And this is the precise sense in which we'd like it to distinguish, right? So I'm maximizing all over polynomials because I want to find the best one. So over all low-degree polynomials, which one has a large mean in the planted distribution, sort of divided by the size of its fluctuations in the null distribution. Right, and if this value is big, this means it should be easy for low-degree polynomials. If it's constant, it should be hard. And then the underlying conjecture here is that degree D polynomials seem to be as powerful as n to the d time algorithms, roughly, for these average case type of inference problems. So maybe this seems like a very bold conjecture, and perhaps it is. But it seems to also be correct on all the examples we've tried. Correct in the sense that it agrees with the existing conjectures and so on. So I think this is a very exciting direction, and I have a survey on this recently. All right, so this is why we think that this smooth trade-off achieved by the sum of squares is actually the best you can do. And so let's talk now about the contributions of this paper. So what we do, like I alluded to earlier, is that for tensor PCA, we're going to give this hierarchy of increasingly powerful methods, sort of analogous to the sum of squares hierarchy, but instead these are going to be algorithms in the style of belief propagation or AMP, so some kind of message passing algorithm that reasons about L-way interactions among the variables. And what it specifically is the Kikuchi Hessian spectral method. So what this means, well, there's something called the beta Hessian. This is a method that was introduced for community detection. And this is just the generalization of that instead of using the beta free energy, uses what's called the Kikuchi free energy, which is sort of a higher level version. And so what we prove is that these algorithms match the performance of sum of squares in the sense that you get the correct polynomial time threshold, but also that entire trade-off of sub-exponential times algorithms. And this sort of refines the physics approach to algorithm designs and sort of redeems it in some sense. Because earlier we saw that the AMP was not the optimal algorithm. So that's more of sort of a philosophical contribution. A more concrete contribution is that the algorithms are substantially simpler than the prior work, as well as the analysis. So this talk, I'll just talk about even order tensors, although we have similar results for odd order tensors and also for the problem of refuting KXOR formulas. Okay, so here is the algorithm. So it's what we call the symmetric difference matrix. So basically what happens is that we're going to build this, we're going to take this number L, which is sort of like what level of the hierarchy we're at, and we're going to build this big matrix. This big matrix is indexed by subsets of size L. And there's kind of this weird combinatorial condition. If you want to build this matrix, you look at the symmetric difference between these two sets S and T that index it. Right? Here's a picture of what symmetric difference is. It's the union minus the intersection. And then you check if that has size P, which was the tensor order. If it does have size P, then, well, we had an observation about sets of that size, so you can plug in that piece of our data, and otherwise you put a 0. So maybe not clear at all how you would come up with this a priori, but the algorithm is essentially just to compute the top eigenvector of this, and then there's a very straightforward rounding procedure to get this back to a vector of the correct length. So the runtime n to the L. This recovers the basic tensor unfolding algorithm as its first level. But then if you take larger L, you can get these sub-exponential time algorithms, and we'll prove that these match the performance of SOS. And what I want to emphasize is that we derived this matrix in a systematic way from this Kikuchi Hessian. So we started with these ideas from physics, took some derivatives of this Kikuchi free energy, and automatically it spat out this, this weird algorithm that you would maybe not come up with otherwise. Here's maybe a bit of intuition for what it's doing. I won't tell you really the derivation, but I can tell you a little bit of what's happening. So here just again is the matrix M. We're going to compute the top eigenvector using power iteration, let's say. And so we're going to imagine keeping track of some vector v and doing power iteration against that. And this v sub s we'll think of as being an estimate of the parity of that set S. And if we just sort of expand the formula for what power iteration does, it will turn out to basically look like a message passing algorithm among sets of size L. So what do I mean by message passing? Well, here this VS is being updated to the sum of a bunch of things coming from these other sets T. So these I'm going to think of as these incoming messages. And what each message basically represents is T's opinion about the parity of S. And the reason you can see this is because this first term is like a noisy measurement of this parity, and the second term from our previous iteration is an estimate of this parity. So when you multiply those together, you're saying something about the parity of S. All right, and so how do we analyze this? Let's imagine the simplest setting where we just want to distinguish between the spike tensor and pure noise. So in that case, the algorithm is just to build the matrix, threshold the biggest eigenvalue. And the key step is just to bound the spectral norm of this matrix in the noise case, when y is just pure noise. This turns out to be basically the only step you need in the analysis. And the way you can do this one step is, well, you just plug it straight into like out-of-the-box Chernoff bound for matrices, right? This matrix has this particularly simple structure where it can be written as a sum of fixed matrices, each with this IID Gaussian coefficient, right? The IID Gaussian coefficients in this case are the individual y sub u's. And so because of this simple structure of the matrix, the analysis is just basically one line. You just plug in this matrix Chernoff bound. So in comparison, the prior work used a more complicated matrix and needed a lot of hard work doing the trace method and so on to bound this thing. Some related work. Some other higher order message passing algorithms have been proposed before. So this is not new, but these do not have theoretical guarantees as far as I know, and we weren't really able to make this particular version work here. Matt Hastings independently came up with essentially the same algorithm as us, using a totally different motivation based on quantum. And this group also independently came up with a different way of, different type of redemption for these local algorithms called replicated gradient descent. So just to sum up, we saw that these so-called local algorithms are suboptimal for tensor PCA. This includes gradient descent and this AMP that only keep track of a single n-dimensional state and are very fast. We saw that you could actually build this hierarchy of increasingly powerful message passing algorithms that keep track of higher beliefs, and that this matches the power of the best known algorithms, which is the sum of squares. And as an added benefit, it was a much simpler analysis than before. And so some future directions are, to unify statistical physics and sum of squares more generally. And we saw here that this was a systematic way that you could come up with an algorithm using ideas from statistical physics. And it would be nice to be able to systematically obtain these kinds of spectral methods more generally. Thanks. Right, so one other example of a problem without a sharp threshold would be planted clique, where here AMP does not quite get the right thing. It gets some constant times the threshold, but really you should expect to be able to make that constant smaller and smaller by perhaps passing to higher levels of the hierarchy. So we haven't proven this, but this, in principle, I would hope it should be true.